right, so let's go through a rundown of the mixtures, acid-base mixtures. I mean, there are only a limited number of combinations. So let's think of the combinations of we could have weak acid, weak base.
Weak acid, strong base.
Yeah. Well, weak acid, weak base. What do we have? What is that? Weak acid, weak base. That would be a what type of mixture? A buffer mixture.
Oh, okay.
And then there are going to be three subcategories of that. What are the three subcategories? What are the three subcategories of weak acid, weak base? HH is one. HH, they're going to be conjugates of each other. The acid and the base are going to be conjugates of each other. And then what else do we have?
You're going to have ones that are not conjugates, like H3PO4 and benzate.
And what was this? And the
Benzate.
benzate? How about like benzoate or something like that? Benzoate.
Yeah, benzoate.
Or some other. Okay, so that's where the weak acid and weak base are unrelated, right? And so that's one subcategory. And the other one is what? Weak acid, weak base mixture. The other one is the one that's the exact same thing, amphoterics. So that's good. And then there are three different ways of handling that. And so let's look at some other mixtures here. We have strong acid. Go in no particular order. Strong acid, weak acid mixture. A strong acid, weak acid mixture. An example of that would be something like HCl and acetic acid, or any weak acid, or oxalic acid. Here, you know, this is an acid mixture, so you just look for hydronium ion contributors, and you do it stepwise. Okay? This is stepwise works. Except, you know, we have the common ion effect, and so it turns out that if you have significant quantities of both HCl and acetic acid, then the HCl is going to dominate the pH. And so this is like a polyprotic acid, and the polyprotic acid you would just do step one. For something like this, we potentially just do step one, the HCl, you know, and we expect very little additional hydronium from acetic. But, you know, how do you know without actually doing it? And so, do you want to do an example of this, or just to see? All right. And so, let's look at something like this. If we took HCl, and let's go with a stronger weak acid, like oxalic acid. Now, oxalic Ka1 for oxalic acid is it's pretty big, you know, and so this could potentially contribute some hydronium. And then what we're going to do is this. We're going to make the solution 0.100 molar in both. This is convenient because, you know, I can skip step I. When I do this, I can skip step I. What was step I? Solution dilution. But sometimes on tests, I might say like this. I might say equal volumes were added together. And so I might say like equal volumes were combined. Okay, and so there are two ways you start. There's problems where you can skip step I because the solution's already 0.1 molar in both. And then there are problems where you have to do step I, which would be the solution dilution. So if I said equal volumes were combined of both these solutions, then what would the concentrations of the final solution be? Yeah. And so the two possibilities are, one, I give you the concentrations in that beaker. So in this beaker, I have 0.100 molar HCl and 0.100 molar oxalic acid. The other type of problem is when I have two beakers and I mix them together. And so if I had two beakers and I mixed them together, then what would the concentration of HCl and oxalic acid be there?
100 over the total
Yeah, 0.100 over the total volume, but I don't give you the total volume, so can you figure it out? Yeah, it's going to be 0.0500 molar, 0.0500 molar, because it's just a 1 to 2 dilution. Do you see that? And so sometimes I might throw that in as an extra twist or something. Or I might give you some volumes and you have to figure out the solution. So in chapter 17, one of the first things we do is we look, are those concentrations, the concentrations in the total mixture, or are those pre-mixture, pre-mixing? And so we have to figure that out. And so far, up to this point, most of the problems would be, these are the concentrations you're going to find in the mixture, and this is what we deal with, And so you got to watch out for this. Watch out, because if this were the case, then
Is it 0.5 or
0.0500 molar. 0.0500 molar, because it'd be a 1 to 2 dilution. Does everybody see that?
Wait, okay,
Mhm.
Why would it be, a 1 or 2 dilution, and how do you know if we have to do,
0.100 divided by 2.
Well,
0.5.
yeah, it would be like this. It would be X milliliters plus X milliliters, because they're equal volume, right? And so the total volume is going to be 2X milliliters. And so the dilution factor is like this. Dilution factor is going to be X, the original volume, over 2X, the final volume, which is just equal to 1/2. Yeah, 1 over 2, so it'd be 1/2 the volume. I mean, not 1/2 the volume, 1/2 the molarity, right? That's what we have. So it doesn't matter what the is. And so this would be like a step I. This doesn't require any dilution. And so if I say 0.100 molar HCl and 0.100 molar oxalic, then we assume that that's the concentration in the mixture, and we don't have to do any solution dilution, so we'll just go from there. And so when we have a strong acid and weak acid, we just do the biggest K first, which would be HCl. HCl plus H2O liquid. This is going to give us hydronium and chloride. Initial, would be 0.100 molar. Hydronium is going to be 0 molar. I'm going to assume nothing's happened. And then we know that, what's K for this?
Very large.
Very large. So we're going to get 0.100 molar hydronium and 0.100 molar chloride. All right, and then we go on to step 2. Step 2 would be the next biggest hydronium ion contributor, which will be what?
The oxalic.
It will be the oxalic acid, H2C2O4 plus H2O liquid. And this is going to give us hydronium and HC2O4 minus. Oxalic acid is a diprotic acid. And so there's going to be a Ka1 and a Ka2 for this. And so oxalic acid will be 0.100 molar, and then we'll carry down the hydronium, and we'll see how much additional hydronium we're going to get from oxalic acid. And so this is going to be plus, minus X, plus X, plus X. And so at equilibrium, we're going to have 0.100 minus X, and 0.100 plus X, and then X. Shoot. Does somebody have their... No, probably you. Okay. John has his book. I just need the Ka1 for oxalic acid.
Ka1 is 5.4 times 10 to the negative 2.
5.4 times 10 to the negative 2. I chose oxalic acid because it has a pretty big K, for a weak acid. 5.4 times 10 to the minus 2. And so if we're going to get some additional hydronium, it'll probably be from something like oxalic acid. If this were acetic acid, which would be 10 to the minus 5, acetic acid would probably contribute negligible additional hydronium to this. Probably ignore acetic acid completely. If we're looking at pH, if we're looking at inventory, we of course take care of it. But this is going to be the hydronium ion concentration times the hydrogen oxalate concentration divided by the oxalic acid concentration. And so we're going to get 0.100 plus x times x over 0.100 minus x. You know, even though the k is kind of big, simplifying assumption may not work here, but might as well just try. And so if we use the simplifying assumption, then x is just equal to Ka1, right? Which would be 5.4 times 10 to the minus 2. 5.4 times 10 to the minus 2 is 0.054 over 0.100, which gives us a 54%. 54% is too big, and so the simplifying assumption failed. That means we're going to have to figure this out using the quadratic formula.
No.
So this is going to be
Who's got that special calculator?
x squared. What are we going to get here?
X squared plus 0.100x
Plus 0.100x.
equals 0.54 times 10 to the negative 2 minus 5.4 times 10 to the negative 2x.
Yeah, okay, so this is 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, so this is going to be 0.0054. Okay, minus 0.054x. So we'll add a 0.054 to both sides.
You get them similar times the Ka value.
Which I did here. Thanks.
Oh, I see what you did.
Yeah.
You did all those.
Yeah, so this is going to be x squared plus 0.154x minus 0.0054 equals 0. All right, so now we need somebody with a fancy calculator, fancy $17 calculator, which is, I guess, you know, for John, John found the, what was that, the $2 scientific calculator. Pretty nice over at the 99-cent store.
Wow. It is on quadratics?
No.
You could,
That's its limitation.
you could buy 8 of those for the price of one fancy one.
It's 5.098
5.098 times 10 to the negative 3. Thanks.
Okay, how do you get that?
By plugging it into the calculator.
That's a fancy calculator. You have to buy one of those. Yeah.
Those aren't allowed in the test anyway.
But you don't have to buy one of these because you guys know the quadratic formula, right?
Yeah.
So if you know the quadratic formula, you're okay. You can get it from the
But
quadratic
I'm
formula.
scared of making mistakes.
0.0949.
What is it? Point
0949.
0949?
Yeah.
Okay, and then over here,
No, it should be easy. What's the negative?
10 to the negative 3 would be 0.10598.
That works.
Okay, so something like oxalic acid, you know, because it's a fairly strong weak acid, does contribute. It contributes about 6% additional hydronium to this, so we wouldn't ignore the contribution from oxalic acid. At least Ka1. What do you think about Ka2? Well, what is the magnitude of Ka2?
I know it's times 10
Oh,
to
10 to
the
the negative 5. 5.3
Okay,
times 10 to the negative 5.
yeah, times 10 to the negative 5, then I'd probably
Let it go.
let it go. Probably ignore Ka2 for this because it's probably not going to give us much. But if I was unsure, I'd just go ahead and do it because it doesn't take that much time, right? And figure out how much additional hydronium. And then there's one more after Ka2, that would be Kw. What do you think about Kw? For sure we could ignore Kw, you know? But we might do Ka2 here. All right, so the book comes up with a simple thing. The book just says, you know, it's going to be the strong acid is going to dominate the pH, ignore the weak acid, but we can't always ignore the weak acid because if the weak acid is fairly strong, then it could contribute a significant amount of hydronium, okay? But this is similar to what we've been doing all along, you know, for these, etc. So I'll let you, I'm not going to finish this, but you know, the point was to see how much, because we want to know the pH of this, right?
Which brings me to, okay, you told us, like in a 0.1 molar phosphoric acid, can we go for K1, K2, or K3? You didn't give us any of those K values. So we gotta determine it like qualitatively?
Well, for that,
You didn't give us any of the K values.
I didn't give you any of the Ka values, but you should know. If you have something like a weak acid, you know, Ka1 might be like 10 to the minus 2, 10 to the minus 3, but what about Ka2?
At least 5, just 7 or 8.
Yeah, 10 to the minus 5, 10 to the minus 7, something like that. And so the only time you'd worry about the Ka, the second step in a polyprotic acid, is if the K value is more like 10 to the minus 2, which is kind of significant.
The X values,
You got a different X value? Okay, what X value you got?
0.0294.
0.0294. Well, you know, I didn't do the double check, but let's see if our double check would have done something here. Let's put in 5.098 times 10 to the minus 3 molar here, and then just double check these concentrations for K, and see how far off it comes.
I'm really scared to do the double check.
The double check's easy, just this times this divided by that.
But what if I'm off? That's what I'm really scared of.
Then you have to do it again. Because that's 5.6
Especially on
times
the
10
time
to
death.
the negative 3.
What is it coming
Yeah,
out?
that's it.
It comes out okay?
It's pretty cool. I got 5.69 times 10 to the negative.
5.69 times 10 to the negative 3. Huh.
I'll do it
versus-
I'll do it one more time to make sure, but yeah, I think so.
If you look at the percent, that's let's say like 60 out of 500. It's like 10% off. Let's see.
Yeah, that's what I got.
0.0294.
Yeah, exactly 4 negatives.
Okay, let's do it.
Oh,
Did other people get what?
no, I'm sorry, I was using the 5.098.
No, you should use the 5.098 because now we're going to look at the 0.0294.
Okay, now we'll check it out.
Check it out. 0.0294. So that gave us a K more than 10% off. And so let's try this one, 294, which gives us 0.0616.
What was
Oops,
that? 6 point.
not 6, this would be 7, right? 716, 706.
How do you do the double check quickly on a time test?
I got 5.38 times 10 to the negative 2. That's pretty close.
5.38 is good because 5.38 would
That's
round to
what I'm saying.
5.4, so
Pretty
that's
close.
good. And so that's with
That's our
the,
double check, and that's our good number.
this is 294,
Yeah.
1294 molar, and then
0.0294.
0.0294 molar. All right, so K comes out to 5.38 times 10 to the negative 3, which is good. The other one was a bit too far off, and so, and you know, if you're off more than 10%, that's probably not round off unless you're overzealously rounding numbers, right?
Yeah.
All right, so you know what? Step 2 here contributed 29% more hydronium. And so here, the weak acid was a significant contributor to additional hydronium in this case. We could go to,
Step 3 now, just to check. 'Cause it was
yeah,
so
okay,
much
let's
step
do you want to do step 3?
I'm asking, is there a simplification that we can say no right away, or yes? I mean, still at 10 to the negative.
All right, two reasons why I'd say step 3 is probably not going to be that significant. Step 3 would be the second deprotonation of oxalic acid. And so this would be the hydrogen oxalate ion hydrolyzing water to form hydronium and oxalate. the first reason is this. The concentration of hydrogen oxalate is 0.0294 molar. The concentration of hydronium is 0.1294 molar. And so look at that, because here, you know, we're going to lose some minus X molar, and then we're going to gain some plus X molar.
There's not a lot to lose from.
Yeah, one, we don't have very much hydrogen oxalate, and two, we got lots of hydronium. So this is like a common ion effect magnified, because it's not just common ion, but it's also a lower concentration of acid here. And so 0.02, this one we could do pretty quick because we could use the simplifying assumption. It should work fine. And so what was the K again?
5.3 times 10 to
5.3 times 10
the negative 5.
to the negative 5?
Yeah, for
Okay.
Ka2.
Yeah. And so this is going to be the hydronium times the oxalate. Divided by the hydrogen oxalate. So this is going to be 0.1294 plus X times X divided by 0.0294 minus X. We're going to just assume X is going to be small relative to both of those. And so this is just going to be 0.1294 divided by 0.0294 times X. And that means X is equal to, what is it? 1.20 times 10 to the negative 5th. Okay, thanks. So we got to look. The percent change, which one will be a bigger percent change? X versus 0.129 or X versus 0.029? Oh, X versus 0.029. So what we'll do is the percent change, we're going to do 1.20 times 10 to the minus 5 divided by 0.0294 times 100.
It's less than 0.4%.
Less than 0.4%?
Yeah, it's 0.04%.
That's very good.
Okay. Less than, yeah, less than a half. 0.04?
Yeah.
Less than 0.05%, which is very good. And so here we got 0.1294 plus 0.0000120. And so did this step contribute much hydronium?
No.
No. And so if we were just interested in pH, you know, I would probably skip this, especially during timed exams, but I wouldn't have skipped this step here. Because I would have known oxalic is, you know, it's fairly strong for weak acid. All right, that's not too bad, you know, strong acid, weak acid mixture. Strong acid, strong base, I mean, actually,
I have a question. If we accidentally chose the wrong acid to begin with, would it disturb in step 2? And that's how we know we started with the wrong acid? Like if we started with oxalic and then we tried to do the hydrochloric, would it totally change the H2O concentration?
no. No.
You know what I mean?
It depends on how you do it.
Huh.
You know, your book is going to skip step 1 entirely. You know how your book would have done this? Your book would have started with oxalic acid. And so the question is, how would you have started with oxalic acid?
It makes it kind of confusing.
Your book would have started with oxalic acid, but they would have done something. They would have said, okay, the oxalic acid is 0.100 and the hydronium is 0.100 molar. So if you started with oxalic, already adding the hydronium from the HCl, then you're okay.
One step.
But if you put 0 here, then it's screwed up, because what's going to happen is you do this and then you do the HCl, that's going to upset this equilibrium, and you got to go back and redo this.
But
And so
if you
you're
do it
going to
that
do,
way, you know that you chose the wrong acid first.
yeah.
Probably.
But you would know because you always start off with the biggest K. Anyway. Okay, so this is more. What was that? B. So see, we're just going to think of all the combinations. Strong acid, strong acid. Probably should have done this one first. This is easy. Strong acid, strong acid. Strong acid, you don't have to worry about any Le Chatelier shift, right? And so you just do, like, for example, if this were 0.100 molar,
Sulfuric acid.
oh, sulfuric is more tricky, of course.
Nitrate.
Is it because dichroic?
Yeah, sulfuric is more tricky because we got to do, okay, we might as well do sulfuric since you brought it up. Let's say I have 0.100 molar hydrochloric, 0.100 molar sulfuric. Which one would I do first? I'd do hydrochloric first. The reason is because sulfuric is diprotic. If this were monoprotic, then it wouldn't matter. But since it's diprotic, the first proton comes off as a strong acid. The second proton comes off as a weak acid. And so this is not a strong acid, strong acid. This is strong acid, and weak acid mix.
Which is inferior.
Yeah, and the problem with the weak acid is kind of a stronger weak acid, like 10 to the minus 2 for the K, right? And so we'd have to worry about it. And so this is
Like H2SO4 plus 0.100 already of the H3O?
yeah. And so we would do K for HCl and K1 and K2 for H2SO4. K2 being the weak acid here. And so this is more complicated. Versus just a strong acid. So if I had just a strong acid, then it's simple. Strong acid would be like 0.100 molar HCl, 0.100 molar HNO3. That's simple because, you know, this is going to give me 0.200 molar H3O plus, and then just add them together. We don't have to worry about it. Okay, so we did strong acid, weak acid. And we have one more, A, B, C, D. We have weak acid, weak acid. Weak acid, we got to look at the Ks for the weak acids. If the Ks are significantly different, then we can solve it stepwise, right? And so,
Let's do one with not significant difference, and let's do one with a significant difference.
that is, if K, you know, if there's a big difference in the Ks, then we could try it stepwise. Unfortunately, if the Ks are kind of close, and then we got to solve it simultaneous, right? So you want to look at an example you've had of both? Or just one?
I want to do it simultaneously. Like, what do you have to do it? Like,
All right, let's think of an acid that would work simultaneously.
Sodium acetate.
Well,
That's not an acid.
we could try something like acetic acid. Acetic acid would be 10 to the minus 5. So what other acid has a Ka around 10 to the minus 5?
Benzoic.
Benzoic? Okay. Let's try benzoic and acetic. Benzoic acid is it has the benzene ring and then the COOH group on them. This is going to be, give me the K values.
6.3 times 10 to the negative 5.
6.3 times 10 to the negative 5, and this is 1.8 times 10 to the negative 5. And so here, we could try it stepwise and see, you know, if it works. Let's just try it stepwise. We're going to make this solution so we don't have to deal with solution dilution. We'll make it 0.100 molar in both, and then see. And so for benzoic acid, C6H5COOH, this will hydrolyze water to form benzoate, C6H5COO minus plus hydronium here. This is 0.100, 0, and 0. So I'm going to not write out the whole table. This is just going to be 0.100 minus x molar, and then x molar. And then K for this is going to equal, so the benzoate times the hydronium divided by the benzoic acid. X squared over 0.100 minus x. Just use a simplifying assumption, should work, which gives us an x of what? One of the professors here outfitted the entire lab with 99-cent store calculators.
Is that golden? I gave him to
No, long time ago. Because this was during the policy where they were saying no graphing calculators, no programmable calculators. Since a lot of students didn't have a regular calculator, did that. Only problem was they didn't last very long. They lasted one semester. Most of them broke, so we ended up throwing them away. But those are the old version, so maybe this new one's better. So what is the x?
2.5 times 10 to the negative 3.
Okay, give me one more digit. You got to get in the habit of going.
Or 2.50.
50 times 10 to the negative 3.
Yeah. And then 2.5%, so it should be fine.
Okay, 2.5%, we're good. It's not perfect. If you want a better answer, use the quadratic. But this should be good enough. And so this is 0.100 minus 0.0025. This is going to give us 0.0975. And then here, 0.0025. 0.0025. All right, then we're going to carry the hydronium down to the next step. Step 2. Let me erase this here. Actually, the acetic acid. So HC2H3O2 plus H2O liquid is going to give us hydronium plus acetate. Acetic acid is 0.100 molar. Hydronium 0.00250 molar, and the acetate is 0. So equilibrium 0.100 minus x, 0.0025 plus x, x. K will equal, you already have it?
The answer to that?
Yeah.
1.34 times 10 to the negative 123.
1.34 times 10 to the negative 3?
Yeah.
Okay. Yeah, so the simplifying assumption is no problem, 0.1% change, or 1% change, 1.3% change. So the hydronium is what we're interested in, 0.00250 plus 0.00134. 0.00384 more.
For third.
Yeah, does everybody see that? This is going to screw up step 1's equilibrium. And that means we have to solve simultaneously, right? But this is a trickier one because we have to solve, actually maybe, can we just solve Ka and Ka and not have to deal with Kw? Or do we have to deal with Kw? In this case, we don't have to deal with KW. KW will be an insignificant contributor. In the earlier cases, we had to deal with KW because we had hydronium hydroxide, and we had to balance those out with KW. Here, we just solve these two simultaneously, which is, again, it's beyond the scope. You just have to recognize it, right? So that was this acid combos, and then we have the base combos, base plus base, right? And that would be what? What letter am I on now? D?
No, that was you're on E. D was weekly.
All right, so I'm on E. The base combos are going to be the same. You know, strong base, you know, strong base, weak base. Weak base, weak base. And the same type of deal, right? It's the same, except rather than looking for hydronium, you're looking for hydroxide. That's the only difference. And you're dealing with KBs instead of KAs, right? And so I'm going to skip this, doing examples of that. All right, so the next A, B, C, D, E, F is going to be this. We're going to look at strong acid, strong base. Strong acid, strong base, this is called a titration, a mixture. And so an example of a strong acid, strong base would be HCl and sodium hydroxide. HCl and sodium hydroxide, this is going to produce salt and water. Driving force, stronger to weaker acid.
Doesn't mean that we can drink it. Right?
Yeah, absolutely right. It doesn't mean you can drink it because you don't know, is that a stoichiometric mixture or is there excess? You know, if there's excess sodium hydroxide, then you're drinking drain cleaner, right? And if there's excess acid, then you're drinking, you're drinking muriatic acid, which is cool
that's
acid.
another name for hydrochloric?
Yeah. And so you don't want to drink it. And so what we're going to do though is this is like Chem 1A stoichiometry, isn't it? You've done lots of problems like this. But the difference here is this. In Chem 1B we do something called a pH titration. And so what we're going to do is we're going to follow this from, you know, normally we add what? The sodium hydroxide and the burette and the HCl in the flask. And so we're going to titrate this. So normally there's going to be excess HCl, limiting reaction to sodium hydroxide until we completely neutralize it. And then we stop, right? But in Chem 1B we don't stop, we just keep going. So what we're going to do is we're going to follow this from just straight acid to excess acid, to neutralization, to excess base. And the way we follow that is by plotting the pH versus the milliliters of titrant. The titrant in this case would be sodium hydroxide. And so if I start off with 0.100 molar HCl, well, what's the pH of 0.100 molar HCl? It would be 10 to the minus 1, so the power is 1. So we'd start off with a pH of 1.00 here. And then as we add the sodium hydroxide, let's say that it's 0.100 molar sodium hydroxide we're adding to this. And so it depends on how much. What happens is the pH goes up just slightly because, you know, the pH is only going to go up slightly because we neutralize a little bit of HCl, but then the solution remains as HCl solution. And so there are different points to this titration. As we get closer and closer to the equivalence point, You know, what's the equivalence point?
It's 1 to 1, so it should be
Yeah, it was
25.
when we stoichiometrically neutralized, you know, at least the one proton there. This is the equivalence point. What's the end point? The end point is where the indicator tells you to stop. The indicator is usually phenolphthalein with light pink color. That's going to tell you to stop. But the end point and the equivalence point are different, slightly.
Why?
I'll show you.
It's gonna stay pink, really.
The equivalence point is when we neutralize all this acid, then we just have salt and water left. This salt is what's the pH of sodium chloride? It's pH 7. And so at the equivalence point, we expect the pH to be 7. But do you know where phenolphthalein changes color? To light pink?
Probably 6.01 or so.
Not at pH 7. Phenolphthalein changes color at pH 9. So we start to see a pink color at pH 9 around here. Here's where it goes light pink. We're off 2 orders of magnitude, you know, because pH is a power scale, so powers of 10. And so we're off 2 orders of
You're
magnitude.
off by 100.
Yeah, but we're off by orders of magnitude in the hydronium, but we're not off by orders of magnitude in terms of milliliters. The amount of error this adds because of how vertical the slope is here is less than a drop. It's less than a drop. And so it's going to turn pink. And then what's going to happen is, you know,
Becomes a hydroxide.
yeah, it becomes a hydroxide solution, and then we just slowly level out. And so we're going to go past this. So this point here is called the equivalence point. That's when we've stoichiometrically neutralized it. This point here is called the end point. You know, it's when the indicator changes color, in this case phenolphthalein. It's going to just stay red. And they're just slightly off, but the error that, you know, the error is less than a drop error between the equivalence point and the end point, so we don't worry about it. All right, so as far as the volumes go, we want to know the volume here. This is called our equivalence point here. And then we divide that in half. For example, this would be the half equivalence point, which is important. And then over here, we could have the 3/2 equivalence point. We just go, you know, another half equivalence point beyond. So we'll have the 3/2 equivalence point. And then we could have the 1/4 equivalence point, the 3/4 equivalence point, etc. And so this would be the 1/4 equivalence point and 3/4 equivalence point. And so what we'll do is we'll do some calculations to figure out these. Titration. All right, what I'm going to do is I'm going to try to keep the numbers simple. And so this is 0.100 molar, and I'm going to put in 10.0 milliliters of 0.100 molar HCl in here. And then I'm going to titrate it with the burette. This is just going to be 0.100 molar NaOH. All right. They're both the same concentration, and so the equivalence point should come in at how many milliliters of sodium hydroxide? 10. And so the equivalence point is going to come in at 10.0 milliliters. And that means the half equivalence point will be 5, and the 1/4 equivalence point will be 2.5, and the 3/4 will be 7.5. The 3/2 will be 15. And so we're going to do some calculations. The way we do titrations, the way I do titrations is always the same. Each calculation I treat as a separate problem. So let's see. I'm going to do the half equivalence point. Let's do that. And then I'm going to insert another one in here. We're going to call this the 9.9. We'll do the 9.99 out of 10 equivalence point. In other words, this is going to be 99.9% neutralized.
2 drops before they.
Yeah, we got to figure out how many drops that is. And then we'll do the equivalence point, and maybe the 3/2. All right, so 9.99 out of 10 is how many milliliters? And so that's 9.99 out of 10 times 10 milliliters, which is going to be 9.99 milliliters.
Pretty darn close.
Some great math.
Yeah, and so it just keeps things, so we're going to treat these as separate problems. So let's just call this problem A here. So problem A is we have 10 milliliters of HCl plus 5.0 milliliters of the NOH. And so what this is going to give us is a total of 15.0 milliliters, right, of solution. And so what do I have to do first?
The step I.
Step I, the initial solution dilution step. And this is before any reactions occurred. So let's figure out the new concentration of HCl. New concentration would be the original volume, 10.0, divided by the new volume, 15.0, times the original concentration, 0.100 molar. So there's a 10 to 15 dilution, or 2/3. So this is going to be 0.0666 sub 6 molar. I'm not going to round here. And then the sodium hydroxide concentration is going to be, it's going to be 5.0 over 10.0,
Oh, wait.
0.100,
15, sir?
oh, 15, sorry, 15.
9.3.
Yeah, so this is going to be 0.0333 sub 3 molar. And so we take, now we do the reactions. Step 1 is the strongest acid plus the strongest base. The strongest acid, HCl, the strongest base, sodium hydroxide. We need sodium chloride plus water. Initial for the HCl, 0.0666 sub 6 molar. Sodium hydroxide, 0.0333 sub 3 molar. Sodium chloride at 0. Change, well, what's the K for this reaction?
Is it very large?
No. Yes and no.
Do we have like?
Yes.
There we go. Sorry, I forgot to add the berries.
Very, very, very large, which means it's complete. What's the limiting reagent? The sodium hydroxide. So this is going to be 0.0333 sub 3. This is going to be 0. This is going to be 0.0333 sub 3. Now,
Okay, I
Is-
know the equilibrium concentration is 0.333 sub 3.
I just subtracted it. You know, this is a limiting reagent, so we lose all of it. So X here is minus point. So this is going to be minus 0.0333 sub 3. This is going to be plus 0.0333 sub 3.
But you got it twice.
Just because of the way it added. This minus this is that, and 0 plus that is that.
So now can we consider the concentration?
It just happened by coincidence.
The concentration.
Don't
of
worry about it, there's
HCl
no
and the
connection.
concentration is H3O.
What's that?
Can we take the concentration of HCl and say it's the concentration of H3O?
Yeah, we could do that, but isn't this an HH buffer? Is this an HH buffer? because I have an acid and its conjugate base. The conjugate base of HCl is chloride. And so I have HCl and chloride. Is that an HH buffer? HCl and chloride, like acetic acid and acetate. Yeah, it's got to be a weak acid. This is not an HH buffer. HH buffer has got to be a weak acid, weak base combination. This is not it. And so this is a strong acid neutral salt. Neutral salt we can completely ignore, right? And then we could just figure out the pH. But so the next step would be Ka for HCl, but
Very large.
you could do that in your head, right?
100%.
It's 100% ionized. So, and then are you going to worry about water, Kw, contributing anything to this? No, not at all. So the pH is going to be
1.48.
1.48. So the pH by halfway is only gone up by 0.5, you know? Actually, I'm allowed 2 sig figs here. 1.48, give me one more digit. Actually, I'm allowed more.
You want more?
Yeah.
Then make it 1.477.
Never round for your first answer. I need to see the rounding step because I got to see how your calculation went.
You do a subset.
So yeah, 1.477,
7.
and then round if you want 1.48. But,
I'm sorry, I thought pH was always just 2 digits. That's not true.
pH is not always 2 digits past the decimal. It's 2 digits past the decimal if you have 2 sig figs. Technically, it looks like we have 3, but I think I only have 2 sig figs here. But it's okay. Sig fig rules, there's a problem with the sig fig rules. And the problem with the sig fig rules is they don't always work.
Well, what do you mean? Like, when does it fail? When does the sig fig rule fail?
When the sig fig rule fails is in a situation like this. The uncertainty is in the, you know, even though this is just 2 sig figs here, the uncertainty is in the tenths. And so when we do this, you know, this one overestimates the uncertainty. If I round this to 2 sig figs, I've just overestimated the uncertainty in the answer. Yeah. That's when it fails. It's back in chapter 1. There's a homework problem that talks about this issue.
When sig fig rule fails, what we're gonna do? We're gonna leave a whole bunch of digits? No final answer?
No, what you do is you do something called propagation of errors. The propagation of errors is discussed briefly in Chem 1A, maybe, you know.
Yeah.
But pretty soon you start doing everything using propagation of errors, which you'll need some calculus to deal with that. And then you don't have to worry about it. All right, let's see how we're doing with time. So at the equivalence point, what are you going to do? Yeah, at the equivalence point, it's plus 10.0 milliliters. And like I said, we start the problem over. And so what we're going to end up with here at the end is 20.0 milliliters of solution. And then we have to do step I, which is the solution dilution, or just do solution dilution. And so the new concentration of HCl is going to be a 10 to 20 dilution of 0.100 molar, which is 0.0500 molar. And the sodium hydroxide, same, 0.0500 molar. And then we take this to step 1, which is 0.0500 molar, 0.0500 molar, 0. Change is going to be complete. This is stoichiometric. This is the equivalence point because we got equal amounts, right? And so the 0, 0, and 0.0500. So we're left with a 0.0500 molar sodium chloride solution. Sodium chloride is neutral, right? And so the only hydronium ion contributor to this is water. And you don't have to do the Kw, right? Because you know the water is going to be pH 7. So let's go to the 3/2 equivalence point. And so that's going to be with 15. So we're going way past neutralization here. And so we're going to add 15 mils. And so we're going to get a total of 25 mils. And so we're going to have to do the solution dilution again. HCl concentration will be a 10 to 25 dilution of 0.100 molar. And the numbers aren't so clean here. What does it come out to? .04. Give me more digits.
That was it. 0.04.
All right, 0.0400 molar. Well, maybe it isn't so bad. And then the sodium hydroxide will be a what? It'll be a 15 to 25 dilution of 0.100 molar, which is 0.0600 molar. Then we just plug that back in over here. We got 0.0400 molar HCl, 0.0600 molar sodium hydroxide, and 0. Limiting reagent here is HCl. We'll be left with 0.0200 molar here, and we'll get 0.0400 molar HCl. And so we got 0.0200 molar sodium hydroxide. Would you worry about the additional hydroxide from KW here? You think KW will be a significant contributor? No. And so we're pretty much done here. What we do is get the POH. Yeah, and so what is the POH of this?
1.69.
1.69. Give me one more digit.
1.69.
Okay, and then the pH would be 12.31.
1, sorry.
And so these are pretty much like Chem 1A stoichiometry style problems. The only thing is when you get very close to the equivalence point. When you get very close to the equivalence point, then the major contributor will be water. And so then we might have to worry, oh, KW might be a significant contributor. And so if I have just a slight excess of acid, you know, it'd be a tiny amount of acid plus KW, right? And so let's go to the 99.9. 99.9, well, whatever, 9 it's a 90, anyway, we've neutralized 99.9%, which means plus 9.99 milliliters of sodium hydroxide.
Yeah.
And so that means we have 0.001. How big is a drop of water?
0.05.
Yeah. 0.05 milliliters. Well, we're 0.01 milliliters from the equivalence point, which is 1/5 of a drop. Can you get 1/5 of a drop?
Not with our equipment.
Yeah. Actually, you can. Do you know how to get a partial drop?
I would weigh it and then evaporate out.
In Chem 1A,
Wow.
you guys don't know the technique for getting less than a drop?
No.
Is it even possible? You know what? It's possible because in Chem 1A, the way you do it is you hang. You just like you get a little hanging drop there. Just and you can make it grow bigger or smaller. And so you just get a hanging drop, but you can't tap it in because it's not big enough to fall, right? And so it's just a hanging drop, and then you get your spray bottle and you spray that sodium hydroxide in. Then you can get less than a drop, right? For Chem 1B, we don't want to do that. We don't want to spray in water because if we spray in water, do you know what happens to the pH? pH changes. And so we cannot get less than a drop in Chem 1B. We're just going to have to get the smallest quantity we're going to get as a drop because we don't want to be changing the pH, like that. Unless it's a buffer. If you're in the buffer region, what we call the buffer region, then adding water is not going to change the pH because, you know, it doesn't change the base to acid ratio. But, well, this is, you know, this is about as close as you can get. Let's say 1/5 of a drop. I might be able to hang 1/5 of a drop there, but, you know, 1/100th of a drop, are you going to hang at 1/100th at the tip of the burette? That's going to be really difficult, wouldn't that? And so maybe this is as small as we can get and as close as we can get to the equivalence point without hitting it. And so, well, let's figure out what the pH is going to be. So here, this is going to yield 19.99 milliliters, let's say. And so let's figure out the HCl concentration. The HCl is going to be a 10.0 to 19.99 times 0.100 molar dilution. 0.0525. 0.05025.
It's 050025. That looks right.
All right, the sodium hydroxide will be a 9.99 out of 19.99 dilution of 0.100 molar.
04997. 04997.
Okay, thanks. Let's plug that in here. The HCl is going to be 0.050025. Sodium hydroxide will be 0.04997. So I'm going 5 digits past. Give me one more digit on sodium hydroxide.
0.049974.
4. Okay. So what's the limiting reagent here? The NaOH. So minus 0.049974. So 5 from 1, 5 from 4 is 1. 12 from 7 is 5. It would have been 9.
I got 5.0012 times 10 to the negative 1, 2, 3, 4, 5.
Okay, so
4 zeros and then 50012.
On the second row.
Yeah, like that. If you want to know the pH, oh wow, didn't like the pH.
all right. Well, before we do that, we got to figure out, is KW
Yes.
going to contribute here?
Good.
Should I, you know, because all of a sudden the hydronium is getting kind of small. Hydronium is getting kind of small. We might have to worry about KW. Should I worry about KW here? No, I wouldn't. Why? Because this is 10 to the minus 5. The most is hydronium I'm going to get is, it's going to be actually less than 10. It's going to be like 10 to the minus 8, 10 to the minus 9. Probably like 10 to the minus 9. Is 10 to the minus 9 going to have any impact on this? No. And so fortunately for titration problems, you don't have to worry about factoring in KW because, you know, the mechanics of the titration, we aren't going to worry about it, you know, basically. This is about as close as we're going to get. And so go ahead and get the pH. What is the pH?
4.3009.
4.30.
09.
2 zeros? Double O?
Yeah.
All right, think about this. This is 1/5 a drop away from pH 7. So we go from pH 4.3 to pH 7 in 1/5 of a drop. Can you believe that?
Dang. I cannot.
Yeah, that's like 1,000 times, you know, change in the hydronium ion concentration or something like that. And it's a dramatic rise, right? It's near vertical. And so in strong acid, strong base titrations, what we see is this. We see a huge jump in the pH near vertical, and this is about like 6 pH units.
Right around neutral.
Yeah, right around neutral in like a drop or 2 drops. You know, within a drop or 2, we go up 6 pH units. Probably within 1 drop. This is why, you know, this is why the equivalence point is pH 7, but the endpoint's pH 9. Is there any big deal? There's no big deal because that's a tiny fraction of a drop error. It is an error, but it's a negligible error at that. And so let me talk just a little bit longer and then break. What we're going to do is in lab next time on Thursday, and we have to prepare for this.
Are you gonna give us a handout?
I was going to give you a handout, but I'm thinking I'm not going to give you a handout.
Then how are we prepared? Off the website? Could be good.
How do you prepare for this? You have to do a little bit of planning to prepare for this. Even if I gave you the handout, you have to do a little bit of planning because the procedure has to be adjusted depending on what you observe. And so what you're going to be given is a weak acid. So what we're going to do is a weak acid, strong base titration. Your unknown acid could be monoprotic or diprotic. We don't know. In Chem 1A, you knew. You know how you knew whether your weak acid, unknown acid were monoprotic or diprotic?
It's on there.
Because it says on the vial, right? It says on the vial. Well, then if it says on the vial, then it's not really an unknown acid, is it? I mean,
Limits to what it
yeah, it limits it to what. Yeah,
can be.
right.
What you'll let us play with.
But in Chem 1B, it doesn't say on the vial if it's monoprotic or diprotic.
Uh-oh.
But in a pH titration, it's really easy to figure out because if you have a monoprotic acid, then we have what's called one equivalence point. That is one jump up. The jump up here for a weak acid is not as dramatic because we start at a higher pH. We're still going to end around the same pH because it's excess sodium hydroxide. But since we start off at a much higher pH, this is like more like 4 pH unit jump.
That's a monoprotic acid?
Yeah, this is monoprotic. The equivalence point is like this. The equivalence point is actually at a pH higher than 9. The pH is going to be, not higher than 9, but higher than 7. And so an example of this would be something like acetic acid with sodium hydroxide. Acetic acid with sodium hydroxide does not form a neutral salt. Sodium acetate is not neutral. Sodium acetate is actually basic. And so we form a basic salt in water. And so the equivalence point is greater than 7. So if we're using something like phenolphthalein, phenolphthalein works, actually phenolphthalein probably coincides with the
It interferes.
equivalence point here.
You gotta use
Closer, it's closer to
another
7.
indicator.
No, phenolphthalein's perfect.
How come?
Because it will show up at 7 at the equivalency.
Because sodium acetate solution, depends on the concentration, but sodium acetate solution will have a pH around 8 or 9. If the sodium acetate solution has a pH of 9 and phenolphthalein changes color at 9, then the equivalence point and the end point coincide. They're the same. And so that's why I say it's perfect. Even if they don't coincide, it's still closer. And so rather than being off a tiny fraction, we're off by next to nothing. You know? That's for monoprotic. Let's say I have a diprotic acid. If I look at a diprotic acid, an example of a diprotic acid would be something like oxalic acid and sodium hydroxide. then what I'm going to see here I'm going to see two equivalence points. One for the first proton, and then one for the second proton. The one for the first proton might be very difficult to see, in fact. It could be, it's not as pronounced. The pH jump here is very small. And here, you know, the pH is still around 3 or 4 units for the second here. The first is a very small change, hard to notice. In fact, some people miss it entirely. Do you know how they miss it entirely?
Go too fast.
They don't
No,
know.
no. The one thing about the handout says take your unknown acid and dissolve it in 100 milliliters of water, or 200 milliliters of water, or 25 milliliters of water. But you know what? That's not what you should do. What you should do is you should take your unknown acid and try to dissolve it in a minimum of water. Because the more water you dissolve it in, the closer the pH goes to neutral, right? And so the problem is if somebody dilutes this too much, you know, then the pH is going to be higher because it's not as concentrated. And so if somebody were to dilute it by following the procedure as written, they would maybe get a higher starting pH because they have way too much water in there and miss this entirely because the pH is too high. It's already been neutralized by the water in a way. And so what you need to do is you need to make sure that the initial pH is as low as possible, because if you make it more concentrated, the more concentrated and the lower the pH, the more pronounced this first equivalence point is going to be.
I actually did this yesterday in sodium chloride. I was trying to make a concentrated solution in sodium chloride by dissolving it in like a little water, and then I'm making a dilute solution by dissolving it in lots of water.
Well, that's exactly what you want to do. You want to try to dissolve this in a minimum of water. So the point one is dissolve unknown acid in a minimum of water so that we can get the pH as low as possible. You know, to make it the most concentrated that we can. There's a problem with this, though. Some people are really good and they can dissolve it, well, not really good. I mean, they just get an acid that's highly soluble. You get an acid that's highly soluble, you can dissolve it in very, very little water. But the way our setup is going to be is we're going to titrate this using a beaker. Not, you know, what do we usually titrate with? Erlenmeyer flask. The reason we're going to use a beaker is this. We need to be able to stick the pH probe in here. And so, two, we have to adjust the water level. Because we have to make sure that the bulb on the pH probe is completely covered with water. So, for example, if the water level were like this, you did a great job, you dissolved the acid in a minimum. Well, there's not enough water to take a decent pH measurement, and we need to get a pH measurement. And so, unfortunately, after all that work, dissolving it in the minimum, now you have to add a bunch of water right here so that the bulb gets submerged.
So should you say minimum height is the height of that bulb?
In any way, we might miss that.
Yeah.
saying keep the concentration strong by adding more acid.
Well, there's a problem with adding too much acid.
Uh-oh. What's that?
The titration is going to be hard.
The titration might be over very quickly. If you add way too much acid, you know, normally you want to use the whole burette in a titration, but some people, they have so much acid that the titration is done in 3 milliliters. After 3 milliliters, let's say after 1.5 milliliters, they hit the equivalence point, and then they just go beyond that. And so that leads to huge relative error in there. And so we have to watch out. We don't want to go too concentrated. And so here, the problem is that some people will add this much water and their acid still does not dissolve. There's some acids that are very tough to dissolve. If your acid doesn't dissolve in that much water, then heat it. Okay, so if your acid does not dissolve in this amount,
How do you know when we should start heating it? Okay, if we just keep adding more and more
You're
water.
going to see little chunks in the bottom of your beaker. Go away then.
you'll know because you're stirring it and nothing seems to be happening. It just doesn't look like it's going to dissolve. It just looks like a cloudy suspension. Other people's acids will dissolve right away, like a significant fraction of it will be dissolved. All right, so we have to make room for the burette. So the burette's going to go here. But if we're not using the Erlenmeyer flask, how do we swirl the solution? The way we're going to swirl the solution is we're going to drop in a Teflon coated iron bar in here. This is called a stir bar. And then on Thursday, we're going to control that stir bar with the stirrer. And so the stirrer, there's a magnet in here that spins.
Oh, that's awesome.
And so you can spin the bar in there.
Or the glass.
What's that?
The negative pressure on the inside of the glass, you don't have to worry about that.
Yeah, you don't have to worry about it. This is going to stir. You don't want to stir too fast that it splatters out of here. And so you just get a stir rate, a decent stir rate. And then we'll take the initial reading. Now the problem is, how much acid should you weigh out? Yeah, go ahead.
So, as promised, I have the Chapter 17 worksheets, so I'm just going to hand them all out. And as you all should know, we're meeting up today. Chapter 17 is what we're covering. So, in the meantime, does anyone have any questions? No questions? All right.
Reading, since I'm not being able to make it, could I do the worksheet? Could I do the worksheet? Chapter 17?
Yeah, if you read the book, it's all lined up with the book, the worksheet.
And then do the worksheet.
So if you don't come to the workshop, it's still okay because everything in the worksheet lines up with the textbook.
In the textbook.
Right. last one? Okay, great. So I'll see you all hopefully today. Thank you, Dr. Smith.
Thanks.
Bye.
Bye.
What?
You actually, how much acid? So before you do anything in this lab, we're going to do a trial titration to figure out how much acid we need. We don't want too much and we don't want too little. Too much acid means we have to refill the burette. Like there are people who've used way too much acid and they had to do like 3 burette fills, 150 milliliters, finally neutralize it. And then there are people who did too little acid, you know, and got 3 milliliters. And they were out of here in minutes. They were so happy, but the results were really bad. You know, they didn't do so well, unfortunately. And so what is the best amount of acid? The best amount of acid is this. And so let's just say optimum amount of acid the best amount of acid would be the amount that would require about 25 to 35 milliliters of titrant. Equals the amount of acid required for 25 to 35 milliliters of titrant. Actually, you know what? Let's just, we'll get rid of 25. We'll just say 35 milliliters of titrant. You know, it's just
Why wouldn't 30 work?
Hmm?
Why wouldn't 30 milliliters work?
30 would be fine too. You want to go with 30?
Then change the range. From 30, 35 milliliters, or 30 milliliters to 35 milliliters.
Should we do 30 milliliters?
No, I like 35.
All right,
Should apply to
35.
the whole number, in my
35?
opinion.
It's kind of too much.
Those 0.5s can be.
Yeah, you're right. Maybe 30 might be better.
Just because of the.
Just because we don't have to. All right. You see, this is arbitrary. But what we want to do is we want to use most of the burette. The burette goes 50 milliliters, so we don't want to go over 50. And what we want is we want this for 30 milliliters of titrant to hit the equivalence point. We don't want to go too high here either because we want to go past the equivalence point so that we see the shape of the entire curve. We need to go at least 10 to 15 milliliters past the equivalence point. To 15 milliliters beyond the equivalence point. And so let me tell you, in a monoprotic titration, the equivalence point here, this is going to have a pH greater than 7. In a diprotic titration, the first equivalence point has a pH less than 7 at the first equivalence point. The second equivalence point has a pH greater than 7. If the pH is greater than 7, what's a good indicator to use? Phenolphthalein. Phenolphthalein is a really good indicator to use. And so it doesn't matter whether we have a monoprotic or a diprotic. What we want to do is we want to hit it's going to be the first equivalence point in a monoprotic, or the only equivalence point, and then it'll be the second equivalence point in a diprotic. And so the trial titration is going to go like this. The vial for the unknown, this is to save you time. is going to give you a range of masses, like let's say 0.100 to 0.200 grams.
That's easier.
And so you weigh an amount between these two and use that for your trial titration. You know, this is so you don't play a guessing game, you know, where you guess and you might guess wrong. You know, it might take you 3 burette loads to titrate it. And so this should only take 1 burette, or maybe a lot less. And so what we're going to do is the first titration, we aren't going to use that fancy stir rod or anything else. We're going to just use an Erlenmeyer. Erlenmeyer flask. And we're just going to do a hand titration. So what you're going to do is you're going to get some acid, this amount, dissolve it in water, add a couple of drops of phenolphthalein.
Cabernet style.
Yeah, exactly. And then just do a quick titration. But be careful because this might not take 25. It might just take 5 milliliters. Who knows? Let's say after this titration, I figure out, oh, it required, let's say it required 22.33 milliliters. And so an example, let's say 22.33 milliliters of sodium hydroxide was required to titrate 0.123, actually we're going to use the Chem 1A balances. So how many digits?
4 or 5, right?
Yeah, 4 decimal places. 0.1234 grams of acid. And so then to calculate the optimum sample size, we do this. We just go X grams over 35, what did we do, 30 milliliters? 30? So X grams over 30 milliliters is equal to 0.1234 grams over 22.33 milliliters. And then solve for X. X grams should be your optimum sample size. All right, the X grams, this is what you should dissolve in a minimum of water. In our trial titration, we don't care because we aren't measuring pH. And so we could add more water in that if we want, no big deal. Okay, now when we perform the pH titration, we want to make sure we get enough data to clearly map out, you know, is it monoprotic or is it diprotic? And so each data point represents a pH measurement. But the problem is this. The problem is if we're just slightly off, here, let's say we're 1 drop off. If we're 1 drop off or a couple of drops off, and we're expecting the steep rise, you know, there's going to be a steep rise that's going to happen within a drop. You could easily miss it, right? Because our calculation's slightly off. So we think it's going to come at 30, but what if it came just a half a milliliter too late or too early? Then we've missed the entire thing, right? And so what we have to do is, in order not to miss it, we need to go drop by drop. And so we should take drop by drop so we don't miss that. Because if we take, let's say we take 10 drop intervals, then we don't know where it is because, you know, there's a big gap right there, right? All of a sudden it just shot up. And does that make sense? And so we have to do drop by drop. But how many drops are there in 50 milliliters? So there's 20 drops per milliliter. So 20 times 50 is going to be 1,000 drops. So 1,000 pH measurements means that there's not enough time, right? because each time you add a drop, you have to wait for it to stir in and then measure the pH once it's stabilized, which takes
5-10 seconds to try at least.
no more than that. Let's say 20 seconds, 30 seconds. Let's say half a minute. 1,000, 500 minutes, 500 minutes. That is not enough time. So we cannot go drop by drop, but we need to go drop by drop. And so what we're going to do is we're going to guesstimate where the rise is going to be and then slow down. Where we guesstimate that range where the rise could be, we go drop by drop. Where there's no rise, we go at bigger intervals. And so this is the way we do it. We expect the big rise at 30 milliliters, but we might be off. So I'm going to slow down before 30 milliliters. And it depends on how accurate you think you were in the trial titration. You might slow down at 28 milliliters and go drop by drop. You might slow down at 29 milliliters and go drop by drop. But around 30 milliliters, you should be going drop by drop. Because this rise is going to happen like this. Boom, boom. And it's over within 2 drops. 1 or 2 drops, it's over. And so we should slow down around this range here. So this would be the drop by drop. And so that's going to come before 30 and maybe after 30. Because what we want to do is we want to capture this whole rise like this.
That's where it comes.
Right. And the other place we want to do drop by drop is around 15 milliliters. Because it might be a diprotic acid. If they're diprotic acid, then if it's monoprotic, then it's going to stay flat here. It's going to be pretty boring around 15. But a little before and a little after, we go drop by drop. And then in these regions, we go, like at a half to 1 milliliter intervals. Is not much happens. And then once we're in the excess, what we call excess sodium hydroxide or excess base, then we'll go at 1 milliliter intervals. And so one of the things that clues you in is the pH. The pH is going to stay fairly flat and then all of a sudden start rising. Remember, to get from pH 4.3 to pH 7 was 1/5 of a drop. So if you're at pH 4, then you got to be thinking you're right on the cusp where it's going to shoot up. And so be careful. And so we're going to take large intervals here and then tight intervals here. And that way we can tell, well, this is a monoprotic acid, but if we had a diprotic acid, it would look something like this. Yeah, double hump. And so what we want to do is we want to make sure we get the first hump, drop by drop, and the second hump. And you have to compensate for, errors in your trial titration, so you better start collecting it. Some people compensate a little too much. They say, I'm not so comfortable, so they start 4 milliliters. They start 4 milliliters before, and they're here. And they didn't finish, and they come in the afternoon to finish it. So you have to look at how much time you have to finish this.
But you will not let us go in the afternoon class, no.
Just try to finish it in the morning. The problem is this first hump might not even be very noticeable. You could have a diprotic, and it's a very, very tiny rise. So it's hard. But whatever it is, however many milliliters this is, it's got to be twice as much to get to here. Stoichiometry. All right, so the primary thing is we want to collect a well-resolved pH titration curve. We call this a titration curve. And in order to get a highly resolved curve, we need enough data, and we need enough resolution to see these features in there. All right, any questions on what we're doing on Thursday? This is all we're doing. We just want to get a good set of data so that we can see these little humps in the curve. That's all. Then we'll analyze it later. All right, no questions. I'm going to stop here and then go ahead and finish that lab we're working on the other day. If you're already done with that lab, you can make another buffer. You can try to make your own buffer, like a pH 5 or a pH 4 buffer with this system.